This is our fifth video on laws of thermodynamics, and in this video I will continue solving problems for you with PV diagrams, and I hope to get through some of the concepts of entropy at our second law of thermodynamics sometime at the end of the video, or maybe second half. So let's look at some of the problems that I did not get the chance to solve for you in the previous videos. In this question, they say a steam engine has a boiler that operates at 500 Kelvin, so that is the high temperature reservoir. The energy from the boiler changes water to steam, which drives the piston. The temperature of the exhaust is that the outside air, 300 Kelvin, so that's the cooler reservoir. So what is the engine's efficiency if it is an ideal engine? And then if 3,500 joules of energy is supplied from the boiler, find the work done by the engine on its environment. So the first one they want us to find is the engine's efficiency. So the engine's efficiency formula is 1 minus T cold over T hot, or it can be 1 minus Q cold over Q hot, or it is work done or the net work done by the engine on the environment over the heat entered the engine. So in our case we have the temperature, so we can plug in the temperature. We have 1 minus 300 over 500. So in this case we have 40% efficiency engine. For the next question they ask if 3,500 joules of energy is supplied, so that is the heat. So the heat is given, and I can use these two equals to each other to solve for B. So I have 1 minus Tc over T hot is equal to 1 minus Qc over Qh, and 1 is going to be cancelled. So I have T cold over T hot is equal to Q cold over Q hot. Now if I plug in the numbers, I have 300 over 500 is equal to, and the heat that is supplied, that is the hot reservoir, so that is 3,500, and we're looking for the cold one. So if I cross multiply, I will get that the Q cold is equal to 2,100 joules. In this question they say a gas is enclosed in a container filled with a piston of cross-sectional area 0.1 meter squared. The pressure of the gas is maintained at 8,000 pascals, so it's a constant pressure. It's isobaric. And then as the result, the piston is pushed up a distance of 4 centimeters. And if 42 joules of energy or heat was added, what is the change of the internal energy of the system? So internal energy of the system is equal to the heat added plus minus the work done by the gas. So the heat added is 42 joules, and piston pushed up, so it's the work on the gas negative, and the work is pressure change of the volume. So I can avoid plugging the numbers for now. So I have heat, and the pressure is given and it's constant 8,000 pascal, and the volume is area times the distance. So I have Q minus the pressure, and then I have the area times the distance that it travels. So now I can plug in my numbers. So the internal energy, the change of internal energy is equal to 42,000 joules minus the pressure, which is 8,000, and times the area, which is 0.1, and times the distance, which is 4 centimeters, 0.04. So that will give me the internal energy is equal to 10 joules. So that's by how much internal energy of the gas increased. And then if the piston were clamped not to be able to move, what is the change in internal energy of the system? So if the piston cannot move and energy is added into the system, so 42 joules of energy is added into the system, but the piston cannot move, then the work done by the piston on the surrounding is going to be gone. So the internal energy of the system is only equal to the heat added because the work is becoming equal to 0. So that would be 42 joules of energy. So there would be increase of pressure in the container, but without moving the piston up or down, the volume doesn't change, so the work is not done and the energy is not lost to the surrounding. So there is a useful thermodynamics variable called entropy, and a natural process that starts in one equilibrium state and ends in another equilibrium state will go in a direction that is causes entropy of the system plus the environment to increase for an irreversible process and to remain constant for a reversible process. So entropy is the measure of a system's thermal energy per unit temperature that is available for doing useful work. Because work is obtained from an ordered molecular motion, the amount of entropy is also a measure of the molecular disorder or randomness of a system. So the concept of entropy provides deep insight into a direction of spontaneous change in many everyday phenomena. Some of the such phenomena would be, and they're called irreversible processes, because let's say if you have an ice and you place it on the stove becomes a hot stove. The stove becomes cooler and the ice melts, but there is no such thing that you can make it back the stove hot and ice cold, or ice to be ice. And another example would be if you place ice in the water. So if there is more heat in the water, the ice is going to melt, and if there is not enough heat in the water, ice will turn the water into ice. And again, there is no such process that will cause, or such phenomena that will cause the irreversible processes to happen. So when we talk about the second law of thermodynamics, we stated that so spontaneous changes for irreversible process in isolated system always proceeds in the direction of the increased entropy or disorder or higher randomness. So here you see a formula given to you. So delta S is change of entropy and equals to Q divided by the T average. And Q stands for the heat transfer, which is positive for heat transfer into and negative for the heat transfer out of the system. And T is the absolute temperature at which the reversible process takes place. And the reversible processes are ones in which all intermediate states between extreme are equilibrium states, and such state can change its direction at any time. And the change in entropy of the system or the surrounding is the quantity of the heat transferred divided by the temperature, like it states in this formula. And the second law of thermodynamics stated that reversible process, the entropy of the universe in contrast, whereas in irreversible process, such as transfer of heat from hot object to cold objects, the entropy of the universe increases. And in the pictures that you see, you have crystal solid, and then you have liquid, and then you have gas. So the entropy is increasing in this direction because the randomness is higher for the gas, or disorder is higher for the gas than it is for crystal. And the same in the next picture, you have highly ordered solid, lower probability. So you will not find the bricks to be fallen in order, they most likely will fall in disorder, so that the higher probability is entropy, not the order. Let's look at some questions where we can use the formula for entropy to do some calculations. So here they say, find the change in entropy of 300 grams of lead when it is melted or melts at 327 degrees Celsius. Lead has the latent heat of fusion, and it gives you 245 10 to the 4th joules per kilogram. And suppose the same amount of energy is used to melt part of the piece of silver, which is already at its melting point 961 degrees Celsius. Find the change in the entropy of the silver. So at first I'm going to find the heat needed to melt lead. So delta Q is equal to, or heat added into the system, equals to the mass of the lead and the latent heat or heat of fusion. So that is 0.3 kilogram. They give you 300 gram, 0.3 kilogram, times its latent heat of fusion, which is 2.45 10 to the 4th. And that will give me 7.35 10 to the 3rd joules. So this is how much energy I need in order to melt lead. But it's all happening when there is a melting process. When you change from one state to another, the temperature doesn't change. So in this case, the temperature is going to stay the same, and that temperature needs to be converted from 327 Celsius to Kelvin. So 327 plus 327 plus 273 will give me 600 Kelvin. So now I can use the formula and substitute the quantities into my formula. So the entropy is equal to the heat added into the system over the average temperature, or the temperature at which the process was happening, and that is 735 10 to the 3rd divided by 600, and that will give me 12.3, and it's measured joules per Kelvin. And for the next part, they say the same amount of energy, so the same amount of energy was given to melt silver, so how much entropy would happen in this case? So the entropy for the next one is same energy, so 735 10 to the 3rd, and the temperature is the melting point is 961 plus 273 will give me 123 point, it's actually 1234 Kelvin. So, and that will be equal to 596 joules per Kelvin. And this example showed that adding a given amount of energy to a system increases its disorder, but adding the same amount of energy to another system in higher temperature results in a smaller increase of disorder, with note to remember. And then this is because the change of entropy is irreversibly proportional to the temperature. So if you have the same processes happening at higher temperatures with the same heat transfer, you have less increase in entropy, whereas at lower temperatures, the same heat transfer will cause higher entropy, higher disorder. So in this question, they say a block of ice at 273 degrees Kelvin is put, 0 degrees Celsius, is put in a thermal contact with a container of steam at 373 Kelvin, which is 100 degrees Celsius, converting 25 grams of ice to water at 273 degrees at 0 degrees Celsius, the freezing point of water, while condensing some of the steam to water at 373 degrees Kelvin. So the water boils at 100 degrees Celsius, so 373 is 100 degrees Celsius. So find the change in entropy of the ice and find the change of entropy of the steam, and then find the change of entropy of the universe. So at first I'm going to calculate the heat needed to melt that amount of ice. So I have the mass of ice that is going to be melted and the latent heat of fusion. So I have 0.025. This is the amount of mass of ice that is turned into water, and times its latent heat, and that is 3.33 10 to the 5th. So I will get 8.33 10 to the 3rd joules. And to calculate the entropy for the entropy increase in the universe, because this amount of ice was changed into water, I have the heat added into the ice to melt it over the temperature when it's happening. So the temperature, again, it was process of melting. The temperature did not change. It's 273 Kelvin that they give you, or 0 degrees Celsius. So that is 273 and 833 10 to the 3rd. And I get 30.5 joules per Kelvin increase of entropy in the universe because of such process. And then for the second part, they ask you to increase of entropy calculate because the steam, when the steam was giving away the heat to melt the ice, some of it was condensed into the water. So I need to find how much heat was lost in this case. So again, I'm going to calculate the entropy. It's the heat that is lost by the steam is the same number, which is 833 when it's lost, 10 to the 3rd. And the temperature at which this process was happening is 373, 100 degrees Celsius when condensation is happening. So I get negative 22.3 joules per Kelvin. So this is when steam turns into water, its entropy decreases because entropy increases with the disorder, and the gas is more disordered, steam is more disordered than water. So entropy decreased by 22.3 joules per Kelvin. But at the same time, this is by how much the entropy of the universe increased, and this is by how much the entropy of the universe decreased. So the total change of the entropy in the universe after steam melted the ice is positive 8.2 joules per Kelvin. It's the difference between those two. And this just shows you that the entropy of the universe always is increasing, as it must in all the natural processes. In this question, they say a chunk of rock of mass 1,000 kilogram at 293 Kelvin, which is 20 degrees Celsius, falls from a cliff of height to 125 meters into a large lake, so also at 293 degrees Kelvin, also 20 degrees Celsius, like room temperature. Find the change in entropy of the lake, assuming that all of the rock's kinetic energy upon entering the lake converts into thermal energy absorbed by the lake. So in this case, I'm going to calculate how much energy the rock had initially. So that is the potential energy of the rock, and that is mgh. So the mass of the rock is 1,000 kilogram, g is 10, and the height is 125 meters. So that will give me 125 and 4 zeros joules of energy. So this is how much energy the rock carried when it was falling into the water. And then if we say that the temperature at which the whole process happened, this is how much heat actually. So this went into the heat. And so the heat that was transferred into the lake. So if all of this happening at the room temperature, 293, 20 degrees Celsius, then the change of the entropy of the lake is equal to the heat that it was transferred, which is 1,250,000, divided by 293 Kelvin, and that will give me 4,266 joules per Kelvin. So this is by how much the entropy of the lake is going to increase. And it also shows how even simple mechanical processes can bring about increase in the universe's entropy. Here's one more example. They say estimate the change in entropy of a tree trunk at 15 degrees Celsius when a bullet of mass 5 gram traveling at the speed of 1,000 meters per second embeds itself in it, and assume that all the kinetic energy of the bullet transfers into thermal energy of all of which observed by the tree. So at first I'm going to calculate how much kinetic energy the bullet had. So the kinetic energy of the bullet is equal to 1/2 its mass velocity squared. So I have 1/2. 5 gram is 0.005 kilogram, and the velocity is 10 to the third, and all of it squared. So the kinetic energy is going to be equal to 2,500 joules. And then to calculate the entropy, or entropy of the change of the trunk of the tree, is equal to the heat, which is 2,500, transferring at the temperature at which everything is happening, the room temperature. So this is 293, again 293 Kelvin, and that will give me 8.53 joules per Kelvin. So again, this is by how much the entropy of the trunk or the universe is increasing, whereby the bullet entering the trunk and transferring its energy, kinetic energy, into thermal energy. Let's solve one more question with entropy before we finish this video. And in this problem, they say a metal spoon at 24 degrees Celsius is immersed in 1 kilogram of water at 18 degrees Celsius. This system is isothermally isolated and comes to equilibrium at the temperature of 20 degrees Celsius. Find the approximate change in entropy of the system. From the information that is given, it's the equilibrium formula from our heat problems. So we have Q1 plus Q2 is equal to 0. And Q1 is the metal, and Q2 is the water. And the change of the energy of the metal plus the change of the energy of the water is equal to 0, because the metal loses the energy and the water gains the energy. And I can calculate how much energy is gained by the water, and that's exactly the energy lost by the metal. And that is M, C, and delta T. So the mass of the water is 1 kilogram, and the specific heat is 4186. That's the number that is good to remember. The final temperature minus the initial temperature of the water, and that will give me how much energy the water gains from the spoon that loses the energy. And that number is 8372 joules of energy. So that's how much energy is lost by the spoon. So I can calculate by how much the entropy of the spoon changed. So that's the heat it lost over the temperature it had, and that's the average temperature. So the heat it lost is 8372, and the average temperature of the spoon between 24 and 20, that's 22 degrees Celsius, but I cannot plug it in Celsius. I have to plug it in Kelvin. So I need to find the average in Kelvin as well. So I have to convert each into Kelvin. So 24 degrees Celsius is 24 plus 273 gives me temperature in Kelvin. That's 297 Kelvin. And 20 degrees Celsius in Kelvin is 20 plus 273 gives me 293 Kelvin. And the average between those two, so the temperature average, is going to be 295 Kelvin. So I'm going to divide by 295 Kelvin, and that will give me the entropy lost, the spoon loses, is 28.38. That's joules per Kelvin. And the same, the entropy gained by the water is the heat over the, so this was the metal temperature average, this is the water temperature average, so that's again 8372 divided by the average temperature of the water, and I get average water temperature is 292 Kelvin. So I'm going to divide by 292 Kelvin, and that is equal to 2867 joules per Kelvin. So this is the energy lost by the spoon, and this is the energy gained by the entropy gained by the loss of energy from the spoon. So the change of the entropy of the universe is the difference between these two, and I get the difference between them is 0.29 joules per Kelvin. And again, you see that the entropy of the universe increases by this much. I have 30-minute limit per video, so I have another few minutes before I have to stop the video so I can solve one more question. So what is the change in entropy of 0.25 kilogram of ethyl alcohol when it is vaporized at its boiling point of 78 degrees Celsius, and latent vaporization heat is given to be 8.5 10 to the 5th joules per kilogram? So I may calculate the heat needed to vaporize this alcohol. So it's the mass of the alcohol and the H vapor. So the mass is 0.25 and the H vapor is 8.5 10 to the 5th. That will give me 2.125 10 to the 5th. And that is in joules. That's the energy needed to vaporize that amount of alcohol. To calculate the entropy, I have the heat over the temperature. The temperature at which the vaporization is happening, so the temperature doesn't change, and the heat needed we just calculated, so that's 125 and 2 more zeros divided by the temperature I have to convert into Kelvin. So 78 plus 273 will give me 351 Kelvin, and that will give me 605.41 joules per Kelvin. So that's by how much the entropy of the universe will increase when you vaporize 0.25 kilogram of alcohol at 78 degrees Celsius when it is the vaporization point of alcohol. I hope these questions will help you to do more practices online, and remember that the more practice you do on your own and solve questions on your own, the better you will understand the subject and more you will learn, and the better you will do on your exams, whether it is AP exam or your college exams. And thank you for watching this video, and I'll see you in the next one.